Good evening, everyone. Tonight we got Jeff. He's going to teach us how to set up our show and the networking part of it so we have a great time with it. Jeff, take it away.
Appreciate it. So I guess I'll start with who I am for people that don't know me. My name is Jeff Garvis. My daughter and my wife and I began our show in 2018 after years of watching the Johnson Family Dubstep show. His HDPE arches that you can see a video on YouTube are still in my show to this day. They were one of my favorite props. But more relevant to the topic tonight, I've worked in the networking field for over 30 years in all kinds of different capacities. I started two of the original Cleveland and Akron, Ohio internet service providers in the late 1990s, back when we used modems to get on the internet. And I've currently worked for one of the largest U.S. telecommunications companies for just over 20 years. And I'm currently I didn't pick this title, the company did, but I'm currently a distinguished engineer in network planning and design. I should point out that my day-to-day functions are actually more focused around voice over IP and call center technologies, but I have a pretty healthy background in networking. I maintain numerous Cisco certifications, and I've passed what's called the CCIE voice written exam. Mostly, I took that a number of times just to renew all of my other certifications. I never actually took a serious stab at the 8-hour grueling lab to get the actual coveted CCIE. This is a pretty poor quality picture of my show from last year. That mega tree in the back right corner was something I've put off for years due to the winds and the hill that thing is currently built on. And as soon as I got it lit, I ran out to the street and took a really crummy cell phone photo. And I can't find a better photo, but that was the first year that we had an actual megatree in our show, and we went big. That is a 32 by 200. So I should just point out real quickly. This is show networking. How to have a show network and just networking in general. And I've done this presentation at the Ohio Lighting Mini that we had at the end of June. There were two of them in Ohio this year. We were the later one in June. And then I did it again at Expo. So I've taught this in two different ways. I've taught it as a very high level intro class. And then at Expo, I did it as an intro and an advanced. And so I've tried to merge those two presentations into one tonight. That may result in some slides not making sense or me saying, oh, whoops, and just skipping that slide. But these topics that you see on here are some of the things I'm going to try to cover tonight. The thing I want to do is I want to give credit to all the other people that have done this before. I've gone out and played all of your videos, all your gem series, your X Essentials. So if you've done this before, I've probably watched your presentation twice in the making of this, and I feel credit is should be given where it's due. So this is a picture that I don't remember when I found it, but I saw this photo and I'm like, I just want to put this in here instead of having to recreate it. I think this is a great depiction of a basic show setup, and I think it helps show what we're going to talk about, which is just the networking aspects of this. So that includes the Pi player there, the switches, and all the controllers and IP addresses that go along with them. We're not going to obviously talk about things beyond the networking aspects of this tonight. So if you're completely brand new to networking, you're probably asking yourself, or maybe you're ignoring the topic because you don't want to have to deal with networking. What is a network? And I think it's important to point out that, generally speaking, networks are just the connecting of devices. But that phrase is very much interchangeably used in the terminology when you're talking about things. And sometimes you'll hear someone refer to a network, but they mean a range of IP addresses. And I am going to get into the nitty-gritty basics of networking when we start here. So if you're an experienced person, I apologize. This may be a little bit boring, but I get into more advanced stuff as we go along. So this is the dreaded OSI layer. If you've ever studied networking or taken any type of certification exam, you've learned this inside out. You've probably created mnemonics to remember the order of operations there on the right. When when I put this deck together, I decided to focus on, just teaching very basic IP networking. So we're going to talk about layers 1 through 4. Layer 1 is the physical layer. It's what, the cabling that's used to connect devices. Layer 2 is where the devices that we're putting on our network are going to use um, hex addresses burned into their chips to talk at the switch layer. And layer 3 is where devices actually have IP addresses. And then there's a little bit of discussion at layer 4 about TCP versus UDP, just because I felt it was kind of relevant to cover it. But I'm not going into deep, stuff with this stuff. I just figured it would make sense to show people the OSI layer model if they've never seen it before. And no networking presentation in this hobby can go without some reference to the actual physical cables that we're going to use to do things. Layer 1 is that physical layer. It's where we're going to use more than likely some type of copper cabling to do connections between our controllers and our switches. And so here on the bottom left, I found this really neat graphic that shows all the different types of network cable that are out there. And I think the biggest thing to point out is the higher the category number, the more speed it's meant to be used at. So in the data centers, where we're pushing 10 gig and up, we're going to need that higher grade category cable today. But in our show networks, I think Cat5e is just completely adequate. But I think the consensus among most of us that know this stuff is just avoid any copper clad or CCA cable. Copper clad is when they put aluminum as the core, and then they basically coat it in copper for the conductivity. That cable is it's going to fail on you, and you're going to regret it, especially if you put it outside like most of us do. And then the only other thing I'd point out on here is the difference between unshielded twisted pair and shielded twisted pair. My opinion is most of us are going to be just fine with unshielded twisted pair. If you're going to go out and purchase shielded cable like that blue one in the photo, you're going to pay an arm and a leg for it, and chances are you probably didn't need it. If you're dealing with a very noisy, maybe high RF environment, and you're having issues with crosstalk or noise, then maybe you do need shielded cable. But I just put that in here to show the difference between shielded and unshielded. I don't recommend anyone go out and buy shielded cable for this stuff. And then I love this picture that I stumbled across. It kind of shows the difference between the categories. You can tell people the higher the category, the more twists there are in the pairs. But this illustrates it really well. On the left is traditional or current modern day 5e. But as you can see in the Cat6 cable on the right, there's more twists to each of the pairs over a shorter amount of distance. And the main benefit that you get out of this is a higher frequency response and a higher speed capability of the cables. And those twists, what they're doing for the cable capability is preventing interference and RFI that could get into that cable, any type of interference. That's what those twists are primarily there for. And then I thought it would be really important to point this out on this slide, specifically for people that are really new to the hobby and might be watching this, tonight or even in the future playing it back on the internet. When you look at the controller that you bought, all of those ports right there will take an RJ45 connector, but they're not all meant to do network, right? So if you plug a network cable into the wrong port, you could cause damage to that controller or to the other ports. So it's really important to know which of your jacks are network cables, which of them are for differentials, or what's for DMX, right? And I think one of the key indicators, at least on this board and most of the Culp-based boards that I've looked at, because on a Culp you're putting a beagle bone on it, is typically your network connector is going to have an LED or two LEDs on it. So if you look in that green box in the top there, those LEDs are link lights and data activity lights, and those are typically where Ethernet should be plugged in, whereas you don't want to necessarily plug Ethernet into those other ports. And I apologize, when I say Ethernet, I meant a connection to your switch. So layer 2, this is the next layer up on that OSI model that I talked about earlier. And layer 2 is also known as the hardware address or the physical address or layer. So when you have a device out there, it doesn't matter if it's something related to our shows or something that you've got on your home network. Everything has a MAC address in it. MAC address is it's, if you're interested in the acronym, it stands for Media Access Control. But this MAC address is basically permanently burned into that device in the chipset when it's manufactured. And it gives it a unique identifier. And if we're getting into the specifics, the left half of that MAC address is going to identify the vendor of that chipset or that device, and the right half is device specific. And the whole purpose for this is when you plug these devices into a switch, it can uniquely identify every device that's been plugged into it and then attribute that MAC address to what port that device is plugged into. So when we're talking about the types of traffic that can be on that network, there's three that I like to point out here. There's broadcast traffic, multicast traffic, and unicast. And the drawing here that I found on the top right, I think is a beautiful illustration of this. So if the red circle in those dots is the device that's talking, say it's your show player, be it a Pi player or xSchedule. If that device wants to do a broadcast for some reason, it would, on the first icon there, you can see all the green circles. They were all going to hear what that broadcast was. If that device wanted to do multicast, it could send that event out, and then just the green circles that you see would participate in that and listen to it. And then unicast is when that red device that's sending something out wants to talk to a specific device, then only that device would hear it. And that's typically being done when you tell something to talk to a specific IP address. So what is an IP address? IP stands for Internet Protocol, and that IP address that you see on the screen there is a unique identifier, and there should be one for every device on your network. So if you're at home, those of you that have printers or any type of streaming thing like an Apple TV or a Roku, they all have IP addresses. Every one of them has a unique IP address. Under the hood, that IP address is created out of 4 octets, and those octets each equate to 8 binary bits that are either 1 or 0 for on or off. But most of you probably didn't come here to learn binary math, so just know that there's 32 bits that make up an IPv4 IP address. But more commonly, people are going to talk about these as the 4 octets, and I'll explain that a little bit when I dig into this just a little bit here. So if we take that IP address and you look at it from what was called a classful approach, look at the class 0 on the top right, and you'll see that the first 3 octets are considered the network, and the 4th is the host. And the reason I jumped down to that one is because typically that's what almost everyone in our hobby is going to use. It's what most of you are probably using at home on your home internet. And what that means is the left 3 octets don't change on a given network, but the rightmost one does, and that's what makes the address unique. If you have a really large network, you could go up to what's depicted there as a class B, where the left 2 octets will stay the same, but the right 2 can change. And that just increases the number of hosts that you can have, or devices you can have in a given network. So there is something out there called RFC 1918 space. That's the more formal terminology for it, but in layman's terms, it's a bunch of ranges of IP space that are reserved for private use. And that could be private use in our homes, in our show networks, or even in corporations. Every company I've worked for that's been larger has a substantial amount of IP space in that 10 range up there at the top. And that works because that 10 network just exists within that company's internal walls of their network, right? The 10 and the 172 and the 192 that you see here, those don't get used on the internet. And when you're using it in your homes, it's unique to your home network. And that's why it works. It's not something that's shared all over the entire internet. So you might wonder, if you're doing stuff in your own show network, why can't you just pick a range of IP addresses? So I put one down there in the bottom left corner, that 204.27.206. That's a class C or a /24. You technically could use that range in your house and for your show networks, and you can do whatever you want with it. But the reason you shouldn't do that is because it might exist on the internet. I can tell you it doesn't because I actually own that block. I registered it back in those days when we were building ISPs. And so you don't want to use somebody else's IP address because it's possible you might want to talk to something on the internet because maybe there's an FPP plugin or something else that your show needs to reach out to on the internet. And if you just happen to pick the network range that those internet resources are on, then your show wouldn't be able to reach those devices on the internet. So let's talk about all those different fields in the settings, the network mask, the gateways, etc. I think I kind of started discussing this in the previous slides, but every single one of those IP addresses that we've talked about belong to a subnet. And that subnet, the size of it, if it's a Class A, Class B, a Class C, or even something that's a fraction of a Class C, the size of the network is defined by that mask that you see in there. So when you see 22255, that means that there's all of the bits in those first 3 octets are quote unquote on, or they're equal to 8 individually, right? So 3 sets of 8 would be 24. That's what's called a 24-bit mask. Most of us, don't think of that at the bit layer when we're talking about these things. But if you put every single device in a given network, if you give it the net mask of 22255.0, then all those devices know that the 3 octets to the left are always going to be the same, and just the 4th octet is where the hosts are. So if this device, this controller you see pictured here, was going to talk to other things, everything else on that particular network would have to be 22255.0. So why do we have a gateway? And I took this screenshot from one of the millions of things that are just out there in our hobby. I don't even know where I got this one from, but this particular example used 192.168.41 as the network. And what this gateway address does is it tells this device if it wants to talk to something that's not in 192.168.41, that its path to get there is via whatever IP address is in the gateway field. And in this case, it's .1, so it's 192.168.41.1. And that's almost universal. Almost everybody does that. Most home internet routers are going to default to .1 being the gateway. But the reason I point this out is if you're just building a network where everything on it is just going to talk to itself, then you wouldn't need that gateway. And the reason you need to understand that is if you're trying to troubleshoot why things won't work, it could be because the device you're trying to talk to doesn't have a gateway, so it doesn't know the path back to you. And that may be the root of the reason that you can't communicate with a given device. So here's a good example of why you need a gateway. If you look at the Raspberry Pi up here that has an address of 192.168.41.10, and that gateway that you saw on the previous screen is that individual's home internet router, and it needed to get out to the internet because you wanted to use Remote Falcon. Remote Falcon's IP address, at least the time that I looked it up when I made this slide, is 104.21.92.63. In order for that Pi to find Remote Falcon, it needs to know that its path to get there is via the 41.1. And that's just an illustration of why you need a gateway. So a lot of people coming into the hobby may want to just set stuff up right away and just make some lights blink. And I think it's important to point out that you don't have to build an elaborate show network just to start playing with your stuff. You can plug a simple Ethernet cable between the Ethernet ports on your controller, whatever brand or version of controller you're using, and plug it directly into your laptop. If you're running Windows or a Mac, it should work just fine, especially on that controller because those 2 ports are actually a switch. So it should link up, and then you can statically configure those devices. That means you're going to pick the IP addresses and nothing else is there to automatically assign it. So you could give the laptop an IP address in like 192.168.1, and you could give the controller an IP address in 192.168.1 as well, one of them being .5 and one of them being .10. This is an option if you just want a real simple way to hook things up and start playing with it. The other option is you could technically plug that controller into your home network if you have if you have a switch with an open port, and you still could statically configure that controller and take advantage of whatever IP address your home laptop or PC already has. But for new people who don't, just want to get to the point of playing with their show, I think this is something that they may want to know about. So let's say you built a Falcon Pi player and you want to be able to find it. So I'm trying to remember when I put this slide at this point in the presentation, so I apologize, it just threw me off. So if you have a fully functional Falcon Pi player, you can put a brand new imaged SD card into that Pi. You can plug it in and turn it on, and just on your laptop or whatever it is. This was a Mac that I was using while I was at Expo, and I wanted to demonstrate this. You can look for the network FPP. If you connect to that FPP, and on my Mac at the time I did this, I had to actually tell it to let me see other networks. It wasn't showing me the FPP network. You can connect to that FPP. It will actually assign your laptop an IP address. And if you go to 192.168.8.1, you'll be in that Pi. And now you can go into that Pi and you can configure it and give it whatever IP address you need for the network that you're going to be on. Or you can see if there's a reason that the DHCP isn't working. And this is one of those examples of a slide that I thought might be out of order, so I apologize. So let's say you have a Raspberry Pi that you need to know its MAC address for some reason. You can turn that Pi on, and there's a couple of ways you can do this. If you hook that Pi up to a HDMI output and just watch it boot, if you remove the SD card, you'll see this screen show up on the right where it won't be able to boot because it won't be able to find any media to read. But it'll tell you, kind of like a BIOS screen on a computer, what its MAC address is. And the reason I put this in here is if you want to add your Pi to a DHCP server and use a DHCP server in your home or in your show network to give your Pi IP addresses, you need to know its MAC address. The other way to do it is you can let it fully boot up. You can log in to the console while that's plugged into an HDMI display, and you can run the ifconfig command, and you'll see on the bottom left there it shows you the MAC address. And the final way is if you do know how to look at DHCP reservations in your DHCP capable router, you can let the Pi fully boot up and obtain an IP address, and you can just go try to look for it in those reservations. And then you can, if you want to do what's called static DHCP or reserved DHCP, you can hard configure it typically in most of those home internet routers. So what's DNS and why do we care? If you've never really dug into DNS, it stands for domain name system. It's the more human readable version of IP addresses. So most of us don't go around trying to get to xlights.org to typing in 6720.112.24, but we can remember xlights.org when we want to go look things up, or if we want to remember the link to get into the Zoom room. Right? So home internet users will typically point their DNS to their ISP just because the hardware that they get from them automatically does that. So in order for FPP to reach things on the internet, such as Remote Falcon, or if you want to use one of the remote access solutions, you're going to need to be able to resolve DNS. So when you're configuring your Falcon Pi player, that's something you're going to want to take into consideration, is how to get it the information it needs to get to DNS if you're statically configuring it and not letting it learn those things via DHCP. Multicast DNS is a really neat solution to devices needing to come up and have a host name so that we can find them without having to build our own local DNS servers within our home. And I think a really good example of multicast DNS is with Falcon Pi Player. If you turn on a brand new FPP and you put it into your network, you can typically find it by just typing in that link there you see on the screen, the http fpp.local. And in most cases, you're going to find that device's webpage. That's a really good way to find an FPP if you have no idea what IP address it came up with, but you're reasonably confident that it's actually come up on your network. If you go into different instances of FPP and you rename them, then that DNS will change. So if I had a culp 32 and I renamed it K32, I should be able to get to it using k32.local. So let's talk about the difference between static versus dynamic, and this is kind of relevant to that reason I was showing you how to find the MAC addresses. If you have a dynamic IP address, that means that when your device powers on, it does a little bit of a broadcast on the local network saying, I would like an IP address. A DHCP server that's typically running on your home internet router would offer that IP up, and then that device would have what's called a lease. Typically they're 8 hours, but that can vary. And then usually if those devices reboot and come back, when they come back, 9 times out of 10, they're going to get the same exact IP address back from the DHCP server. The other option is static, and that's when you go into the LCD panel or via the web page, and you manually choose the settings of that device. That's a little bit more rigid, and in order to change it, you have to go back through that manual process. And what I was alluding to earlier is reserved DHCP or static DHCP. And that's the idea where you tell the DHCP server, every time you see this MAC address come up, I want it to always have the following IP. And that's, in my opinion, very helpful, because when you're building things, if you can predictably know the IP address of the controllers in your network, then in my opinion, it makes it easier to figure things that are going to talk to them. Everything from xLights to any other area where you might have to actually put an IP address in. And here's an example of me configuring reserved DHCP. I happen to have Ubiquity throughout my house, but this isn't unique to Ubiquity. If you go into almost every consumer grade home internet router, you should be able to find a way to go in there and say, every time this MAC address shows up, I would like it to have the following IP. In the screen on the right here, I told it every time it saw that pi ending in 3E57 for the MAC address, that it should always give it 192.168.1.226. So what is the difference between TCP and UDP? So TCP is a connection-oriented protocol, which means when it comes up and you want to talk between two devices, the initiating device is going to say to the far end, I'd like to talk to you about something. The far end is going to acknowledge that, and then the initiator is going to actually acknowledge the acknowledgement. We call it the three-way handshake, and it's time-consuming. But the benefit of TCP is it's relatively guaranteed communication. If that handshake doesn't take place or the acknowledgements don't take place, then the protocol will natively retry up until a limit. UDP is connectionless, and what that means is a packet is put on the network and we hope it gets there. If it doesn't, that's unfortunate. We're going to send more, but we're not going to resend the one that didn't get there. And the reason I think people need to know the difference between these is in our shows, we're very time sensitive. We're talking about 20 to 40 milliseconds or greater response time in our shows. We don't have time for TCP to go do this type of back and forth. So everything, or almost everything we do in our shows is UDP based. Now, if you're accessing the web page on a controller or the web page on a Falcon instance, that's going to be a TCP event. It's a back and forth TCP protocol. What I'm referring to here when I say UDP is strictly the packets that get streamed if you're streaming your show content. And the thing I'd like to point out is multisync is easily confused with multicast, if you're not familiar with the differences between the two. Multicast is a concept of basically broadcasting something to every device on the network. Multisync is something that exists specifically for our hobby. It's a feature in FPP and I believe xSchedule to basically convert a show from the scenario where you're sending every single packet out of a sequence file to distributing that sequence file to all of the controllers and then using synchronization packets that are very tiny compared to the actual show data to keep all of those controllers in sync. And so that's why it's called multisync. So if you, I guess I kind of jumped the gun and explained most of this before I advance the slides. So if you think of a show that has 3 or 4 controllers, I'm just going to use my show for example. I have a Culp 32, I have a Culp 8, and I also have a Falcon 48. When my show is playing, the primary player has to send all of the actual show data to the Falcon 48. That's going over the network if I like it or not. But the Culps that are on my network are running FPP, it's just the way they work. And I actually take the same exact sequence files that are in the main show player and put them on all of those Culps. So my Megatree is a Culp 32, and I have some columns on the porch that are 3600 nodes that are hanging off of a K8. Those 2 controllers have the sequence files on them locally, and my main player will send out synchronization packets to those controllers. And the benefit is a substantially smaller amount of network data. So the Falcon 48 is getting every single show update packet from the F sequence file in real time in UDP packets, and the Culps are just getting a little tiny packet saying you should be at this moment in this sequence, and it just keeps repeating for the duration of that sequence. And just let me wrap up on that whole multisync topic. The reason I explain this is if you're looking at your network and thinking it's undersized or too small or not fast enough, multisync solves that, right? So if you're looking at, oh, do I need to go out and buy gigabit switches and put fiber in and have all kinds of bandwidth? My personal opinion is absolutely not. If you're using multisync, you don't need a lot of bandwidth because all you're doing is sending little tiny synchronization packets. If your show isn't massive, you don't even need gigabit switches because you're not sending all that much data. I think it's between 9 and 32 megabits. But that also brings up the point of Wi-Fi. So just to go back to that whole concept of layers in the OSI model, Wi-Fi is commonly believed to be at the layer 1 or layer 2 level because there is no physical connectivity with a wire, but Wi-Fi is technically at layer 2 because it's also working as that data link layer. Most of you may know this if you've done anything with Wi-Fi. I think you can't really get through your day without connecting to some access point somewhere. But all Wi-Fi networks have an SSID, which is basically the name of that network. And the devices that bridge that gap from the wireless world to the network physical layer are called access points. Some of us have access points basically built into our home routers. Some of us that go the more extreme route, like I have with Ubiquitys, have multiple access points all over our house just to properly, blanket the area with Wi-Fi. But at the radio level of Wi-Fi, there's different spectrums or bands. So the initial band that came out with Wi-Fi was 2.4 gigahertz. 5 gigahertz came out and made some improvements, and Wi-Fi 6 is going to be even better. I found this really cool diagram of what those channels look like. And one of the things I kind of harp on when it comes to Wi-Fi is if you're using 2.4 gigahertz, you really need to know, and to some extent even 5 gigahertz, you really need to do somewhat of a site survey and try to determine what's making noise on your Wi-Fi, because it's really possible that your neighbors are making all kinds of noise that could be detrimental to your show. And then the 6 gigahertz here, you can see that there's going to be substantial amounts of channels and availability as we get into 6 gigahertz in the Wi-Fi world. But for today, most of you are probably going to be working in just 2.4 or 5 gigahertz, if that. So what's the difference between a router and a switch? And I think this is kind of important because I think it's an easily confused issue for people who they don't do this every day and understand the difference. So routers like this Ubiquiti you see up in the top right, they're meant to be a gateway between different networks. So it could be different IP addresses or different physical networks. I happen to have one of those in that top right picture. The nice thing about this is it actually has 2 LAN connections on it. So one of them says VoIP under it. You don't have to use it for VoIP. And the one to the left of the VoIP one says LAN. You could theoretically plug your show network into like the VoIP port on that router and your home network into the LAN. and they would be physically isolated, and they could have different IP addresses. And then in order for you to get between the two, the ubiquity could do it. But the whole point of this slide is to depict that routers are for routing between networks, um, whereas a switch is a device with a whole bunch of ports on it, or maybe just a few, and it's meant to connect a bunch of devices um, to a common network or what's potentially a virtual network. And the difference is, in a router, you're passing packets at layer 3, which means you're talking IP to IP. And in a switch, you're basically talking frame to frame, or I'm sorry, MAC address to MAC address using what's called frames. One of the things I feel is really easily misunderstood in our hobby is how switches actually work. When a switch powers on, it starts listening for all the devices on that switch to start announcing their MAC addresses. And it will, over time, not necessarily a long time, but over time, it will build a database of which MAC address is associated to which of those physical ports on the switch. And then it uses that knowledge to limit what ports see what frames. So if you had two computers, I'm plugged into that little 8-port switch there in the top, and they wanted to talk to each other after the switch had learned everybody. The only ports that are going to pass any traffic are the two that are necessary. And the reason I like to point this out is I think there's a lot of misunderstanding in our hobby that you can overwhelm a switch or you can overwhelm your home network and not be able to watch whatever it is you want to stream, or others in your house can't stream while your show is running. And as long as your show is talking through a switch in this manner, technically there's no reason that a show would overwhelm your internet router or overwhelm your switch. Now, if you're not just going through the switch, then there's something to look at there, which we can talk about. But switch port to switch port, there's no reason you couldn't run a show alongside your home network and they wouldn't necessarily conflict with each other. There is a difference between managed and unmanaged switches, and that could be an entire 1 hour plus presentation that I think we can just sum up with. A managed switch allows you to do a bunch of elaborate functions that are typically going to be way beyond what most of us need unless we're building a large commercial show, or if you're maybe trying to do an elaborate neighborhood-wide show or something over a large number of multiple acres. If you're just using a switch to connect a bunch of controllers in your show, an unmanaged switch is just fine. What you can do in those managed switches is you can go in and do what's called creating VLANs, and there's a plethora of other functionality you can do to all the ports in a managed switch that are way beyond anything we need. And technically, I would argue, and there may be people that disagree with me, if you have a relatively modest size show, you can probably get away with a 5-port 100 megabit switch because you're not really generating all that much traffic. Now, there is the topic of VLANs, and I've seen it come up a lot, and I think I just want to illustrate it here so that if anyone is thinking about VLANs and doesn't understand them, at least you could have a better idea of what they technically are. A VLAN is going to require you to have a managed switch, and what that does is it allows you to go in and say, the ports I've selected here belong to this VLAN. So in the picture, I made 3 theoretic VLANs. The left 8 that are colored blue are for a show. You can see they get to be in 192.168.41. The middle 8 are for maybe you have security cameras at your house. They go in a completely different network that's 10.10.10.1, which also has a different subnet mask. I gave it a 23 just for illustration. And then off to the right, I put 8 ports in a home VLAN. What you're basically doing when you build VLANs is you're making the equivalent of multiple switches in a single chassis. So those ports that I colored, and I just grouped them the way that I did, let you make switches within a switch. It is one way that you could isolate a show network from your home network if you really wanted to, but I would argue unless you know what you're doing and you have a really good reason, it's probably overkill. And that brings me to something I saw posted in the xLights support Facebook group when I was building these slides. I don't know who Bill is, but I kind of agree with him. You don't necessarily need a show network, but it's not going to stop us from talking about it, right? You may choose to do it, and there's a whole bunch of pros and cons, and I'm going to try to go over them a little bit. So, what is a show network? In my opinion, a show network is when we create some type of isolation between the network used for our light show and what we use at home to stream the internet, to watch, to watch TV, to remote into work and do our jobs. It's the isolation of those two networks. I think there's a lot of pros and cons. I also think there's a lot of misinformation, or maybe it's just differences of opinion. In my opinion, the number one pro for doing a isolated show network is physical security. If you put a switch outside of your house that is connected to your home network and you haven't isolated it, then you're exposing your home network, your printers, your internet connectivity to the outside. And someone nefarious could come up there and connect into that and do things that are not necessarily something you want. And I think, it eliminates any concern that you might have about bandwidth, but I think a bandwidth is not the concern that a lot of people make it out to be. I found some people who've already discussed this. I didn't want to recreate it, but Paul Thomas went out and used Wireshark, which is a network analysis tool that we use in the industry and in the hobby, to look at actually what was taking place. He built a 10,000 pixel simulated show at 40 frames per second, and you can see that it ranges from 9 megabits to 14 megabits per second, which is completely insignificant if you're using a 100 megabit switch. And if he converted that show to using Multisync, it was roughly 1 kilobit, which is literally nothing. So you don't necessarily need to do a show network for the purposes of bandwidth, but I do think you may want to do it for the purposes of physical security. The con to doing a show network is that it may very well be unnecessary, and it may be potentially complicated for people who don't feel comfortable in this field, and their time may be better spent working on their show. So I'm going to go through a couple of show networks. One of the things I want to point out, and this is something I think others have said in their presentations on this topic. If you open up the Falcon Pi Player manual and you go down to the appendix, there's a really, really good in-depth analysis of all kinds of scenarios, similar, if not identical, to some of the ones I'm going to go through here real quick. You may find those useful if you want to look at them, or you might like the way I've done it. But there's 3 different types that I think are worthy of talking about, and that's a standalone, completely isolated show network. Just really simple. You're just going to have a switch and your device is plugged into it. I think those are useful if you're going to do a parade float, or you want to light your camper up. I saw somebody a long time ago say they were going to bring xLights out and do something at a school play. I think that'd be your standalone network. Your home-based network is basically when you just let your show coexist with your home, and then the separate show network is when you have 2 separate ones. So I'm going to dig into them with a little bit of topologies here and go through them real quick. So that scenario 1 is if you're just going to use your home network, then you're just going to plug everything into that home switch. So it could be your PCs, your home internet router, your controllers. If you look at the drawing here, I have the home internet router depicted as a separate device from the home switch. That may be something that you have. You may also just have multiple switch ports in the back of your internet router, and you may choose to use those. If you run out of ports in the back of a home internet router, you can run a Ethernet cable from your home router's switch ports to another mini switch, and it will basically extend the capacity that you have there. So if you run out of ports, that's an option. But like I said in the previous slides, because I don't believe that, because of the way switches work, I don't believe you will overburden your show or your home network, that I think you could do this if you wanted to. The only reason that you may create issues is if you routed things through your home internet router and it had, if it traversed your home internet router in a way that it hampered its ability to talk to the internet. That's the only case where I can think of where your show network could limit your ability to talk to the internet. And then if you're going to do Wi-Fi, it is important to know that you can run into issues with performance on a Wi-Fi network, and I'll try to talk about how you can look at that near the end of this. The second scenario is you can just run your show completely isolated. So you have your home network doing one thing and you have your show network completely separate from your home. It's an easy way to do it if you want to do it, but it complicates maintenance of your show. So you're going to have to sneakernet and sneakernet, for those of you that may not know the phrase, is basically you're going to have to walk the data out to your controllers. So if you want to update your sequences or if you want to make changes to the configuration of your controller, you're going to have to take a laptop out to that isolated network, plug into it, and then update it, and then go back, take that laptop back to your home network. And then that scenario 3 is separating your show networks with a router. So you can put a router between two different networks. In this depiction, I showed doing that with a Raspberry Pi. So to this day, my show actually looks like this since 2018. I have a Raspberry Pi with two network interfaces on it. One network interface is my house. The other network interface is my show. I haven't changed that up, even though I'm a network guy and I could do it with a far more elaborate system. But I kind of like it, and it kind of works. So you can use a single Pi as the bridge between them, and to this day, mine is my primary show player. But what you accomplish by doing this is you can have xLights running on your home computer, and you can talk from your home network over to your show network if you want to do updates in xLights, push output changes to your controller, or even push sequences using FPP Connect. And then a little bit later, I'll explain how you can route between those two networks because you do need to create that. Another way you could do that is, like I kind of talked about earlier, is if you have a home internet router that allows you to separate networks like that USG from Ubiquiti does, you could use that device to separate the two networks. You could have a show player that's on that show network, or it could just be some other instance of Falcon player on any other controller. It doesn't have to be a standalone. And you could have basically accomplished the same thing here using a home internet router that has two or more LAN ports if you wanted to do that. Now, and I will explain how to route in a future slide here. So here we are, actually. When routing between those two networks, so in this case, what we've done is I've taken 192.168.1 and I've put that on the home network. And just being consistent with that first screenshot I took, I used 192.168.41.0 and made that the show network. So you'll see everything that's on the left side of this drawing is in a 41, and the home PC down there in the bottom right, or the laptop, is 192.168.1.10. So in order for this to work, that laptop has a gateway configured on it that tells it anytime it wants to get to a network other than 192.168.1, it needs to go through the USG. And the USG knows how to get to 192.168.41 because it's physically plugged into it. So let's say you're on that laptop in the bottom right, and you want to either get to the web page on one of those controllers, or you want something to talk to one of those controllers. Those controllers on the bottom of the screen need to have a default gateway configured in them, and in this case it would be the IP address of the USG, so 192.168.41.1, and that's how those controllers would know in order to respond or reply back to the laptop, they need to go back through the USG to get there. I did kind of illustrate this on the previous slide. The Falcon Pi player or Falcon player can be a show router. I don't know why I put this in here twice. But this is basically a very similar slide to the one I did 3 or 4 slides ago. I think I duplicated this slide, so I apologize. This is something that some of you who may be interested in adding static routes to your laptops may want to screenshot. So if you're going to not do routing at the device that's bridging the two networks. So for instance, let's say you're not going to do it in your home internet router, or you can't do it in this case in your home internet router, because in this particular drawing on the right, the laptop's default gateway is going to be 1.1 on the right. So it's going to use its default gateway to get to the internet. So you can't tell that laptop, hey, your default gateway can be a device that knows how to get to 41. So you would have to actually tell your laptop how to get to the opposing network. And the way we do that on Mac and Windows is we add static routes into those machines. And if you don't tell the Windows or Mac to make that route persistent or permanent, then the next time you reboot it, it will forget it. So the commands that I illustrated on this slide have everything you need to make that route add permanent in those devices. And if you didn't have enough time to screenshot that or write any of that down, just throw the question in the chat and I can come back to it. So the other option you can do is you can use the FPP proxy function in xLights to tell it, hey, in order to get to these controllers that are on the left, use this IP address that I've put in here for the proxy to get to the opposing side. This is a feature of Falcon Player, and I think it's another way that you can accomplish talking from a home network to a show network if you want to just limit, if you want to do it, this is just an easier way to do it. The reason I'm an advocate of doing it in a more broader sense is if you do it through a router or through something that's more device independent, then it doesn't matter which device in your house you pick up. If you want to get to something like a web page that's on your show network, you could pick up any iPad, any iPhone, Android, or any laptop, and then you could just get to the devices. If you're just going to do all of your show maintenance from a single device, this is a perfectly adequate way to do it. So now that the whole debate over 12 volt versus 5 volt has been long settled, I do want to just peel back the discussion of Wi-Fi. I'm a network guy. I've been a network guy forever. I'm a firm believer that wired networks are superior to Wi-Fi. My show is still 100% wired, but I'd be lying to you if I didn't tell you that there are some amazing people and shows out there that use Wi-Fi. And one of them is actually in the state I'm from. I'm from Ohio. Lucy Depp Park is about 2 hours south of me. They have a show that is a roughly 10-acre property, and it's a road. It's a one-way road that goes through a hill and does basically a U-shaped loop. And I think they have 7 or 10 different properties on that loop that are all involved in their show. And the only way they could have done that was with a well-deployed Wi-Fi setup. If you were to try to do that wired, it could be accomplished. It would just be really expensive, and you'd probably have to use fiber to pull it off. But maybe you just want to light up some trees directly across the street from your house. Wi-Fi would be a perfectly valid way to do that. But I think in order to do shows with Wi-Fi, we need to just have a little bit of an understanding of the things we might want to look at. You can't just turn it on and hope it works, right? So there are such a thing as channels in Wi-Fi, and I kind of alluded to that on a previous slide. And in 2.4 gigahertz, there's actually very few channels, and some of them actually overlap with other channels. So one of the problems you could have here if you're deploying your show in 2.4 gigahertz is you might be talking on a channel that your neighbor is just decimating with traffic. And so every time your devices want to talk, they're going to have challenges at the radio level, not even at the network level, where every time they want to talk, your neighbor is just, and maybe it's multiple neighbors, they're all just decimating one of those channels. Some people have reported issues with microwaves intermittently causing issues here. So one of the things you can do is a site survey, and you can try to determine which channels are better for your show. The other thing I would point out, it's even spelled out in the Falcon Player manual, that if you're going to do Wi-Fi, you should be using Multisync. That's the best way to guarantee your success when you are using Wi-Fi. And so I kind of alluded to the Wi-Fi collisions at the radio layer. And I forget where I found this text from, but it was from some industry webpage about how Wi-Fi does try to do collision avoidance. And I took the slide out here, but there is something called multi-user MIMO. Wi-Fi is evolving in a way where it is going to be better at dealing with this and allowing multiple devices to simultaneously use the channel and the spectrum. But we're not there yet, I don't think, as an industry, and I think just the Pi 5s are just starting to become capable of that. So what you can do is you can get tools to look at the impact of Wi-Fi in your area. And one of my favorite tools is called Wi-Fi Analyzer. You can run it on Windows or Android. Unfortunately, you can't run it on Apple products. But you can see from this drawing, you can take Wi-Fi Analyzer and walk around, and the graphing that you see on this page will change as you walk around based on the signal strength that Android or Windows-based device is hearing. And what I find useful with this is it tells you what channels are saturated with a lot of noise and which channels are more likely to be available. So if you're actually going to go do Wi-Fi, or if you're already deploying Wi-Fi and you're having trouble, do something like this. Just a little bit of site survey legwork might help you get better Wi-Fi performance. And if it doesn't, go back to wired. And I think that's all I have in the slide deck. So if anyone has any questions, I'd be more than happy to try to answer them. And if not, I appreciate all your time tonight.
Anybody have any questions for Jeff?
No, great job, Jeff. Thank you.
Appreciate it. Anyone have any corrections?
Other than it's time to ditch the USG and upgrade.
I am a creature of it's working, don't touch it, but I agree with you. It is way time to upgrade.
Well, Jeff, I want to say thank you. That was a great presentation, and hopefully that helps a few more people out there this year. So, thank you very much.
And if anybody has any questions or needs any help, my contact info is here on this slide. Be more than happy to help you. If you want a more timely response, probably stop into the Zoom room and get an answer that way.